Hello and welcome. Today we'll be integrating the tan x family, starting with the tan of x and just do the first few powers just to see how we're integrating this particular function. Okay, let's go with the tan of x first of all. The integral of that dx. Okay, the standard way, and this is not an enrichment lecture or anything like that, is to actually use to write as a sine over cos and use a substitution. So I'm going to show that first of all. So that's of course sine of x over cos of x dx. And this is a substitution workings. We're going to call u our denominator. U is equal to the cos of x. Differentiated du by dx is minus the sine of x. Make dx the subject, so dx is du over minus sine of x. And now we're putting our bits and pieces in. Okay, the sine of x, we're going to leave it where it is because we can see it's going to cancel with that. So sine of x left alone. The cos, we called it, of course, u. And our dx is, of course, du over minus the sine of x. The sine of x is now will cancel, and we end up with a minus inside the integral 1 over u du, which of course will integrate to minus the log of u plus a constant. And of course we can put a substitution back in, and this will give us minus the log of cos of x plus c. And in the formula booklet, this integral is actually given in most formula booklets for most exams, but it's actually showing it slightly different, and I just want to show you where it's coming from. So we can continue. That's done basically. That's good enough. We can actually say, all right, we can actually move this negative using the rules of logs, cos of x to the minus 1 like this, plus c. We can actually flip the cos now, because cos to the minus 1. Careful, because cos to the minus 1 I will never write. This is not the same as r cos. This is basically this quantity here, which of course is 1 over cos and is not the r cos. Careful. So that's going to be the log of 1 over the cos of x. I just use the minus to flip that upside down, plus c, which of course we now can write it as a sec, because that's the definition of a sec, plus c. Okay, so that is how we integrate in the tan of x if we have to prove where it's coming from. An alternative to that, for people that are a little bit more advanced, that don't actually need to use a substitution, so this is now an alternative, just a couple of lines, not really that hard, is to use the fact that bottom differentiates to top kind of result. So we're trying to use the result basically. If you have a fraction and the bottom differentiates to the top, it's a standard result, very easy to prove, is of course the log of your denominator. So this is almost there. So at the moment, if we look at cos differentiates to minus sine, we don't have a minus, so in order to accommodate a minus, I'm going to rewrite it again. Cos of x, stick a minus there because we need it, but in order to balance it, put 1 on the outside, and now is of the form bottom differentiate to the top. The minus, that's the minus on the outside, is of course the log of your denominator, which of course we got this result after the substitution, etc, etc, etc. Okay, so that is now the tan of x. We're going to look next at tan squared. Okay, how do we integrate the tan squared of x? Has it got similarities to what we just done? The answer is absolutely none. So it's done a completely different way, and that's what makes integration difficult really. It's not one size fits all like differentiation. If you know how to do tan squared, differentiate tan squared, you will know how to differentiate tan cubed and so on. This is now a little bit different. We're going to use this identity here. Let me just write it in blue on the top right of the board here. 1 plus the tan squared of x is identically equal to sec squared of x. This identity is very important when we're integrating secs and tans sometimes. Okay, so we're going to switch the tan squared using this identity to sec squared of x minus 1. Why we want to do something like that is because the differential, and I'm going to write another result. Let's do this in orange. I'm going to write on the side here, d by dx of the tan of x is equal to the sec squared of x. And although the tan squared does not integrate, the sec squared integrates back into a tan. So of course that integrates beautifully. That comes from differentiating a tan of x, that's this sec squared, tan differentiates to sec squared, and of course minus x plus c. And that's the way we integrate the tan of squared of x. Okay, let's look now at the tan cubed of x. So that's number 3. All right, tan cubed. What can we do with this particular one? Tan cubed of x dx. We're going to write it as a tan of x times a tan squared of x. That's the nothing major. And why do I want to do something like that? Because I'm going to use this identity again to write it as tan of x, and the tan squared again is going to be a sec squared of x minus 1, which of course I can multiply out now on the next line as tan x sec squared of x minus the tan of x dx. Now, this is two separate quantities and they both integrate instantly. I'm not going to go obviously and just show workings again for integrating the tan of x. This is in the formula booklet, so if you just need it, suppose you had to do the integral of tan cubed, you can actually use the standard result, which says the integral of tan of x, as of the formula booklet, and we just proved it of course a few minutes ago, is the log of sec x plus c. So this is for the integration of that. Now the question is what happens to this particular one. By the time we hit now tan cubes, we're a little bit more advanced. We should be able to do this by recognition, okay? So let me just write the answer. You can actually, I'll do it, I'll put an extra line just to show you something. I can split this integral to tan x sec squared x dx, so that's this bit here, minus the integral of the tan of x dx. This formula booklet, so it's quotable, formula booklet, this bit here, and for this you can actually use substitution separately. If you go just to separate integrals, not that difficult. Use substitution, u is equal to the tan of x. How would you know to use the tan of x and not perhaps sec of x or sec squared of x? Well, the answer is if you are very good with your integration, you won't even need a substitution. That's the first thing. If you're not so good or if you're a beginner, then you try tan of x. If it doesn't work, try sec x. If sec x doesn't work, try sec squared. This is how you do it. Don't expect something magical perhaps that should tell you that's what you always do. You try things. And if you try u is equal to tan x, it will work very, very nicely. For those who are now advanced in integration, I'm going to actually integrate that, and I claim that this comes from differentiating a tan squared. A tan will differentiate, now if we differentiate that, a 2 will come to the front. It will bring the tan of x down to the tan of x to the 1 times the differential of the tan, which is a sec squared. So this quantity that I've got there differentiates to 2 tan x sec squared x. I've got everything except that 2. So I need to get rid of that 2 by putting a half in front of it. And this is what you will get if you do a substitution. And of course, minus the log of sec of x plus c, which again, perhaps you can write, if you don't like a sec now because we've got a minus, you could perhaps write it, not necessary of course, as a plus and write it as a cos, because it's probably nicer to write it like this. Okay, so just a little recap of this particular method. Swap tan squared, swap the tan squared into using this identity to sec squared minus 1, multiply your brackets, perhaps split your integral into 2 bits, this from the formula booklet, or you remember it like most people do, and for this either use a substitution or recognize it. And the rest of the powers of tan are pretty much the same. So let's look at the tan to the 4. I don't know, maybe I'll do tan to the 4 and finish it. Maybe we'll look at tan to the 5 and finish it there. It doesn't really matter. They have the similar patterns. So let's look at tan to the 4 of x dx. What you would do with something like that. Okay, this is the key identity for powers of tan. So let's write it as tan squared of x times another tan squared of x. And what we can do there is swap one of the tans. It doesn't really matter, of course, which one. Let's say we swap the second one, so that's using the identity sec squared of x minus 1 dx. Multiply our bracket, so we're going to get tan squared x sec squared x. We just done similar integral to that, minus a tan squared of x dx. Okay, this particular one will integrate as it is, okay, or with a little substitution. This one, we've done already the tan squared of x, and rather than just quoting the result from before, well, I can't quote it because I don't even remember it. So we're going to rewrite this again. So it's a lot of dribbling, left, right, try to tease the ball. So tan squared is sec squared x minus 1. So I'll just replace that tan squared back into sec squares, because this, of course, will integrate dx. And now this will give us tan squared x sec squared x minus a sec squared of x plus 1 dx. I claim everything integrates instantly. For this, I'm not going to use a substitution. Tan to the 4 is not really for beginners. It's highly unlikely they will give you something like this to integrate on the standard paper without any structure, and therefore I will just quote the answer from there. Okay, to get this, you differentiate the tan cubed. The reason is that it works because, of course, next to the tan squared we have its differential, which is sec squared. This will differentiate to, of course, 3 tan squared x times the differential of the tan, which is sec squared. We got that, except that 3, stick a third in front of it to make it work. This, of course, is a standard result. Tan differentiates to sec squared, so that's going to be a minus tan of x, and of course plus x plus c, and that's tan to the 4. Okay, tan to the 5. Let's start the tan to the 5. I don't know if I want to take it to the end. It's just to give you an idea, basically, of the general pattern with tans. What's the likelihood of getting a tan to the 5 on your exam, on a standard A-level exam? None, really. It's quite silly, really, to give you to integrate tan to the 5. That's purely just for fun. Now we're just doing this. Okay, how are we going to do that? We're going to split it as a tan cubed of x times a tan squared of x, perhaps, because, of course, a tan squared can switch to the differential. Okay, so let's swap now this tan squared to a sec squared x minus 1 using this identity. Then when we times it out, dx, I forgot to put it, let's actually write it here, we have enough room. Tan cubed x sec squared x. The level we're in at the moment, we're not going to integrate tan to the 5. We should be able to see that this is integrable, but of course we're creating a minus tan cubed of x, which is just fairly repetitive, because now we need to do exactly the same thing with that. So let's break it bit by bit. Let's do it very quickly. Sec squared x. Now this, we're going to write it as a minus tan of x times a tan squared of x. That's the tan cubed. And of course, that's the beauty of having a whiteboard. I'm going to replace this tan squared, so I can easily rub it off. I do recommend whiteboards like the one I'm using here for your general work. Costs peanuts, really. It's between £4 and £8, really, this kind of stuff. And this pen is very, very fine. It's really beautiful to write with. Sec squared x minus 1, so that's the tan square replaced. So tan cubed x sec squared x, multiply the bracket, minus tan x sec squared x, that integrates instantly, and then of course plus the tan of x, and of course that's the standard result, and the integration is taking place now. To get this, I need to differentiate a tan to the 4. This is the differential of the tan there, sec squared, with a quarter in front of it. This, a tan with a sec squared next to it, that starts from a higher power of tan, so that's a tan squared, x with a minus a half in front of it. And to get a tan of x, with the standard result from the formula booklet, is of course log sec x plus c. Okay, I hope you found this lecture interesting, this whole lecture lesson perhaps, and you'll join me real soon for another one. I am signing out now.